Hello, welcome to the course Transportation Network Analysis. So, this is the lecture 16 here. So, in the last class, we were discussing about genetic algorithms. So, we had started to look at this example problem max 1. So, this max 1 problem is to find that string that has maximum number of ones if the size of the string is specified. So, this is a trivial problem because, for example, if L is equal to 10, we had seen that having 1 1 1 1 like this 10 times is the optimal string. So, we actually do not need genetic algorithm to solve that, but as you will move along, you will understand that this problem is very useful to understand the concept of genetic algorithm. Okay. So, even if we suppose did not knew that this is the best solution, and if we had to start with some random solution, then where will the genetic algorithm take us to? So, that is what we want to see here. So, every solution in genetic algorithm is encoded as a string of L binary digits or bits. Okay. That is, a solution is represented as a string of L binary digits or bits. Okay. For example, this is one solution here when it is given that L is equal to 10. So, the fitness f of a candidate solution string to the max 1 problem is the number of ones in its genetic code. Okay. So, since we want to maximize the number of ones that are present in any given string or solution, so that is why we are setting the fitness value of a string to be equal to the number of ones that are there in that. Okay. And just to remind you again, so we will be using these terms solution and string interchangeably in the genetic algorithm. For example, the fitness of this string that is given is 6 here, because the number of ones that are present here is equal to 6. Okay. Now, as we had mentioned that in genetic algorithms, we usually start with the population of randomly generated solutions. Okay. So, let us start with the population of n randomly generated strings or solutions. Suppose that it is given that L is equal to 10 here. So, there are 10 digits or bits in the string, and n is equal to 6. So, here n is the population size or the number of strings that we want in every iteration of the algorithm. Okay. So, we are deciding that we keeping 6 strings in each iteration of this algorithm. So, how to generate these 6 strings initially when L is equal to 10? So, that can be done by tossing a fair coin 60 times and then getting the initial population. A fair coin means that it has half probability of getting tails and half probability of getting heads. Okay. And why do we need to toss it 60 times? Because there are 6 strings here and each string has 10 digits or bits. So, therefore, 6 times 10 is equal to 60. So, suppose after tossing the coin, we get these strings here from S1 to S6 here. These are the corresponding fitness values of different strings that we have here. For example, the number of ones here is equal to 7 and the number of ones here is equal to 5 and so on. Okay. So, once we have generated the initial population, the first step here is to do selection. So, there are various methods for doing selection. One of the methods is called the Rowlett wheel selection here. You might have seen what a Rowlett wheel means. So, a Rowlett wheel has these different pies or slices here. So, these pies or these slices need not be of equal size. So, what we do here is that we randomly select a subset of the strings based on their fitness. Okay. But when we select them randomly, we are not selecting them uniformly at random. That is, we will be giving higher likelihood for selection to that string which has higher fitness as compared to a string that has lower fitness. Okay. So, a string I will have probability to be chosen equal to fi divided by summation fj, where j is going through all of the strings that are present. Okay. So, here in our case we have decided 6 strings to be present here. Okay. So, how is it connected with the Rowlett wheel here? Suppose if n is equal to 6, so then we will be having a Rowlett wheel here which will be divided into 6 pies here. Okay, and you can see that these 6 pies that are present, they need not be of equal size. Okay, for example, suppose this is this slice or pie which is corresponding to the first solution. Okay, so this angle that is present, this will be proportional to the fitness value of that string I. Okay, so this angle that will be there will be equal to the fitness of this string I divided by the sum of the fitness of all of the strings multiplied by 360 degree. Okay, so this angle will be proportional to the fitness of the corresponding string. So for example, for the 6 strings that we had initially generated from S1 to S6, the probability of choosing string S1 is equal to 7 divided by 34, because 7 was the fitness value of this first string and 34 is the sum of the fitness values of all the 6 strings that are there. Okay, so in this way we can calculate the probability of choosing these different strings here. So now we have set up this roulette wheel. So in the roulette wheel, in this example that we are considering, we have 6 slices here and every slice is proportional to the fitness value of the corresponding string. And since we want to get a new population, so we are interested in getting 6 new solutions here. So we will be running this roulette wheel 6 times. Okay, and we will put a marker in this roulette wheel. So wherever we run a roulette wheel and whichever slide comes to that marker, that is the solution we will be selecting. Okay, so this is same thing, that we select each new string through this procedure with replacement of strings in the original population and stop when we get n strings. Okay, this thing is important with replacement. What does this mean here is that, for example, suppose we ran the roulette wheel and we got some particular strings, say S2. Okay, now when we will be again trying to get the next solution, we will not be removing this string 2 from that set that we already have. Okay, so it can happen that this string 2 can again be selected. Okay, so suppose after doing this procedure which is called selection, we get the following population here. So we again now have a population of 6 strings here, and you can see that we have S1, S3, S5, S2, S4 and S5. Okay, so the string S5 is getting repeated here. Okay, and that is fine, because when we were selecting these strings here, we were doing it with replacement of the original population. So that is why we can get a string twice, and it can also happen that a particular string may not be selected. For example, S6, which was there in the original population, that did not get selected here. Okay, so this is a randomized procedure for doing selection. So it can happen that the total fitness value that you get for this new population can be higher also as compared to the total fitness value of the original population. It can be same also and it can be lower also. Okay, so this is a randomized approach. However, in the long run, it will happen that the solutions that have higher fitness value, so they will have a higher slice or pie in the roulette wheel, so they will have higher likelihood of getting passed on. Okay, so even though, I mean, if you look at a particular instance, it is possible that the total fitness value of all of these strings might reduce as compared to the original population, but in average, I mean, on the long run, it will happen that the strings that are fitter, that is, they have higher fitness value, they will have higher likelihood of also getting selected in the next population. Okay, so the second step here is called crossover. So in this, we mate the strings that we get. Okay, so now that we had 6 strings after the selection, so we will be pairing these strings here first. So suppose you pair up the first 2 strings, then the third and fourth string and the fifth and sixth string, and before we decide to do crossover, we need to check whether it is satisfying the chance of doing crossover or not. Okay, so there is something called a crossover probability. You can denote it by PC here. So we will be tossing a biased coin which has different values of getting heads and tails. Okay, so for example, if we set the crossover probability to be 0.6, then suppose we can set the probability of getting heads to be 0.6 and the probability of getting tails to be 0.4 here. Okay, so when we will toss this coin, if it happens that we get a head, then we will decide to do crossover for that pair of strings, otherwise we'll just keep those strings as it is in the next step. Okay. So, suppose for a given pair of strings we decide to do crossover after doing this flipping of coin, then we need to decide that how to do this crossover, that is how to generate the new strings or offspring strings, you can say, or the child strings. Okay. So, in order to do that we need to decide some crossover points in the strings. So, we will randomly extract the crossover points. For example, suppose these two are the crossover points 2 and 5. So, let us see what do we mean here. Suppose we want to perform crossover on the first pair of strings S1 dash and S2 dash. Okay. So, before the crossover, these are the strings here S1 dash and S2 dash. So, these are the strings that were generated after the selection procedure. Okay. Now that we have decided to have these points of crossover 2 and 5. Okay. So, again these 2 points were picked randomly from all of the points that are possible here. So, that is why you will be seeing that we have this portion from 2 onwards till 5 in the first string S1 dash colored as red, and this portion in the second string is colored as blue. So, what do we do now is that after the crossover, this red part here from the first string will go here and this will come here. Okay. So, you can see here that this first string after the crossover, it has 1 1 which is the same as 1 1 here, then it has this 1 0 1. Okay. And after that it is having the same thing 1 0 1 0 1 here. Okay. Similarly, in the second string that gets generated after the crossover, this part is the same here, and this part has been obtained from this part, okay, from the first original string, and this one comes as it is here. Okay. And similarly, we will be moving forward for deciding to do crossover on these two pairs. So, for this pair of strings also S3 dash and S4 dash also, we will again first decide whether we want to do crossover or not. So, for that we will be again flipping a biased coin, and if it lands head, then we will decide to do crossover, and suppose if it lands head, then we need to also decide what are the crossover points around which we will be doing the crossover. Okay. And then similarly for this pair also S5 dash and S6 dash also. So, after doing the crossover, the final step is to apply random mutations, okay, in the strings that we have. So, for each bit that we are copying to the new population, we allow small probability of error for it to change. Okay. So, this is called, for example, this small probability of error is called the mutation probability. You can suppose denote it by PM. So, suppose this mutation probability is 0.1. Okay. We usually set the mutation probability to be on a lower side as compared to the crossover probability. So, crossover probability is usually above 0.5 and so on, whereas mutation probability is kept to below, so that we do not change these strings too frequently. Okay. Okay. So, suppose these are the strings that we had obtained after doing the crossover. Now, we want to do mutation on these strings. So, what we will be doing here is that we will be going string by string. So, here in the first string that we generate after mutation, we will be first deciding that this first digit or bit in this string S1 double dash, whether this needs to be changed or not. Okay. So, again since the mutation probability is set out to be suppose 0.1 in this case, so we will be flipping a biased coin. Okay. Now, here we can set the head value for this bias coin to be 0.1 and the tail value to be 0.9 here. So, if we flip this coin and suppose it lands tails, so then we do not change this. Okay. So, then we will keep it as 1 as it is. Okay. Then we go to the second position. So, here again we flip the coin, suppose it again lands out to be tails, so we keep it as it is. Here and here we do the same, suppose we again get tails. Okay. And similarly here also. So, for the first 5 positions we got tails. Okay. Now, for the 6th position, suppose we flip the coin and now we get a head. So, now since 1 is present here, we will make it to 0. Okay. And then we will continue flipping the coins for the remaining positions that are here. Okay. So, we do this for every position here and for every string. So, we will be flipping the coins 60 times here, and whenever we get a head here, so then we will be changing that bit here. So since there was 1 here, so we flipped it to 0. For example, here, since there is 0, we will flip it to 1 if we get a heads here. Okay. So this is the set of strings that we get after doing mutation. So suppose that in this example that we are looking at, the total fitness value changed from 34 to 37. Okay. So what does total population fitness means? So we are adding up the fitness values of all of these strings that we have in a particular population. So in the beginning, when we had randomly generated these different strings, then the total population value was 34, and after doing this selection, crossover and mutation, the total population fitness comes out to be 37. So we see that there is an improvement of 9% here. However, just to tell you that there is no guarantee that after every generation of this algorithm, the total population fitness should only increase. Okay, it can as well decrease also, because all of these operators such as selection, crossover and mutation, they are probabilistic algorithms. Okay, so it can happen that in a particular instance the total population fitness can reduce. Okay, but in the long run or in the average case, it will be observed that the total population fitness will move towards the increasing trend only. Okay. So at this point we will repeat the same process all over again if the termination criteria is not reached, until that termination or the stopping criteria is met. Okay. So for example, we may set a termination criteria that as soon as the total population fitness becomes within say 1% of what we started with, then we can decide to stop and so on. Okay. So when we say that we repeat the same process, then what we mean here is that this last population that we got, that where we had S1 triple dash, S2 triple dash till S6 triple dash, so that will now again undergo selection, then crossover and then mutation, and then we will again check for the termination criteria whether it has been satisfied or not. So this is saying the same thing, that is, if the termination criteria is not met, so we go to step 1, which is selection, and then we go to crossover and mutation. Okay. Therefore, the main steps of a genetic algorithm are as follows. So we first generate an initial population, we set the iteration n to be equal to 1, then we do selection, after that we do crossover of the strings, and then we do mutation. Okay. So in the selection, we select a new set of strings based on their fitness level. So the strings which are fitter, they have higher likelihood of getting selected. In crossover, we pair up these strings and then we do crossover, so we get new combinations of the strings that we originally had, and then mutation, we make some randomized changes across these strings so that we can get some different solutions. Okay. And then in step 4, we will replace this current population with the new population that we got after mutation, and if the required number of iterations have been reached, then we stop, otherwise we set n equal to n plus 1, and then we go to step 1. Okay. Step 1 is this selection procedure. Okay. So one thing to point out is that all of these steps are very important and they have their own advantage. Okay. For example, selection is useful for ensuring that the strings which are fitter get passed on, that is the strings which are moving close to the optimal solution, they get passed on to the next generation or iteration, and crossover and mutation are responsible for generating diverse solutions. Okay. So the selection procedure ensures that the population moves towards the optimal solution as the generations or the iterations proceed, and this it does by prioritizing the selection of fitter strings. And crossover and mutation operators ensure that the population does not get stuck towards a local optimum solution, and thus these steps introduce diversity in the population. Okay. So one more point to be mentioned is that mutation is specifically useful in the sense that it can generate some solutions which might not be even be possible by using these selection and crossover, because selection will only provide you a set of strings which are kind of subsets of the original population that we had in the beginning. Okay, I mean the one which you had in the previous iteration, and crossover will kind of generate some combinations of the strings that you have. Okay, but these combinations itself might not be enough to generate the optimal solution. Okay, and therefore that's a place where the mutation comes. Okay, so we discussed this method of roulette wheel selection before. So in this roulette wheel we had seen that it is a game of roulette, so each string gets a slice of the wheel, but more fit strings get larger slice as compared to less fit ones, and this wheel is spun n times to get n new strings. Okay, that is we are doing this with the replacement here. There are also other selection methods. For example, there is something called tournament selection. So in a K tournament selection, K strings are randomly selected from the current population, and the string with the highest fitness is then finally selected. Okay. So for example, if it's a 2 tournament selection, so suppose we have to generate 6 strings because we have set n equal to 6. So what we will be doing is that in order to generate the first string, we will be randomly choosing any 2 strings because it is 2 tournament selection, and whichever one has higher fitness we will put it there. Okay, again we will go back to the 6 strings that we had, and then we will be again out 2 strings at random and then choosing the one which has higher fitness value, and we will be keep doing this a total of 6 times. Okay, so this process is repeated n times to get a population of size n. Okay. And then there is this method called elitism. So here the most fit strings of the current generation are carried over to the next generation unaltered. Okay. So this method has been found very useful among researchers because it ensures that the best strings of each generation are retained. Okay. Otherwise such strings can be lost if they are not selected to reproduce or if they are destroyed by crossover or mutation. Okay. So as I had mentioned that in selection, operation, crossover and mutation, there is no guarantee that you will always be generating better and better strings. Okay, it's because these are randomized approaches, so you can also sometimes, for example, after the selection method, the best string might not even get selected in the population that you select. Okay, so in order to take into account these things, there is this procedure called elitism where a few of the best strings are kind of stored in the beginning. Okay, and those strings are then not going through selection, crossover and mutation. Okay, only the remaining strings will be undergoing that. For example, if you have n strings in the beginning and 2 strings you decide to keep for elitism, the best 2 strings, that is the strings that have the highest fitness. Okay, so the remaining n minus 2 strings will then undergo selection, crossover and mutation, and once that completes, whatever new n minus 2 strings you have, now you will be combining it with the top 2 strings that you had stored for the elitism. Okay, so in this way you will always be ensured that you never lose the best strings that you had in the beginning. Okay, so you will either be getting some strings which are still as good as what you had before, or you can only get better, but you will not lose the best string that you have. Okay, so with this we'll end the discussion for this lecture, and we'll be continuing in the next lecture. Thank you.